Good morning to all of you. Today, last time we discussed RSA cryptography and various problems on them, right? So in this class, I'm going to confine to RSA cryptography related to, as you know, it is depends upon this problem, right? Factoring of integers. That is a hard problem. Today we will see other hard problem, and based on that, what we can do, right? So for example, Alice and Bob. So I am talking about the Diffie-Hellman key exchange, right? Since Mehak is here, she recall everything. Yeah? Alice and Bob selects large prime, right? Selects large prime P. Since we discussed, I'm going little fast. And a primitive root alpha. Correct? And so this P comma alpha made public. Right? Yeah. Then what Alice and Bob will do, right? So first Alice so chooses random x and computes. Yeah, so okay, let us say, and Bob chooses random y, right? The generally this 1 comma less than or equal to x comma y less than or equal to p minus 2. Okay, so Alice and Bob choose also to random. So only Alice knows x and Bob knows y. These two are public, at x and y are private for Alice and Bob respectively. Now what Alice will do now? Okay, so Alice will computes. Alice sends what Alice sends? Can somebody recall?
Alpha raised to x mod p.
Alpha power x. Of course, everywhere mod p is there. Okay, correct. Alpha power x mod p sends to Bob. Now Bob, what he will do to this? So computes alpha power x power y, because Bob knows it. So he will get alpha power x, right? Now what Bob will do, right? Bob sends alpha power y mod p to Alice, right? So what Alice will do? Computes alpha power y power x. X knows to Alice, right? So you'll get alpha power xy. So this alpha power xy is now the key, right? So alpha power xy is the common key. Is the common key. So key is exchanged. Okay, what now Eve knows now? Somebody help me. In this entire process, Eve knows what? Yes, she knows alpha, she
Alpha
knows
p.
beta, p, alpha power x, alpha power y. What she want to know? Want to know what?
Alpha raised to x1.
Alpha raised to xy. So alpha power xy wants to know alpha power xy. Yeah, but is it possible? So there are two type of problems. So for example, from alpha power x, okay, mod p, okay. So this is equal to say beta, right? So yeah, beta 1, let us say beta 1. So now what is logarithm of beta 1 base alpha? It is x, right? So finding x is difficult, right? This is called discrete logarithm problem, correct? Discrete log problem. Similarly, beta 2 is equal to alpha power y. She needs both of them, or she will find only one of them? Can you guess? Is it necessary that she has to find both? X as well as Y.
No, sir.
Okay, why? How?
Because it is because we have alpha raised to x or alpha raised to y. So
Hmm.
just calculating x or y will give me the answer.
Very good. Very good. Yes. Thank you. Yeah. Yeah. So if Eve computes, if Eve computes X or Y, then she will get alpha power xy, right? Right. That is easy. So no need to compute both of them. Yeah. So, but what is the problem here? So after knowing after knowing alpha power x equal to beta, it is difficult to find x. That is discrete log problem, right? So once discrete log problem is done, then she will find out. But what is this problem called? So Eve knows alpha power x, alpha power y, but from these two, she want to know alpha power xy. This is difficult, but this is not the discrete logarithm problem. Discrete logarithm problem is different. If alpha power x is known and alpha is known, okay, alpha power x and alpha are known. Finding x, finding x is discrete logarithm problem, right? Now alpha power x is known, alpha power y is known, okay, are known. Finding alpha power xy. What is this problem called? Hmm? Yes, this is called DHP. DHP means Diffie-Hellman problem. Yeah, this name, this problem is called Diffie-Hellman problem. Is it okay? Is it two problems are different or not?
Yes, sir.
Yeah. So it
Hello,
the
sir.
Diffie, yes.
But Eve knows alpha as well, right? Or no?
Yeah, Eve knows alpha, Eve knows beta, Eve knows alpha power x, alpha power y. But she does not know how to compute x, how to compute y, how to compute alpha power xy also.
No, I mean alpha he knows, alpha or x he knows. Then he can compute by discrete log, right? X.
If she discrete logarithm problem is done, then it is possible to find out DHP.
Yes.
Yeah. So what you said is correct. So DLP implies DHP, right? Once you found
Yes.
you discrete logarithm problem is solved, then from that I'll find x and I'll do alpha power y power x. I have to find either x or y, as Mehak already told. So once discrete logarithm problem is easy to solve, then DHP is solved. But DHP implies DLP, still it is open, not completely clear. Whether DHP implies DLP or not, still not clear actually. Yeah, lot of work is going on, right? Okay. So these are the items. So today we are going to discuss more depth here, how to find, are there any choices for P where this DLP problem can be solved, things like that. Okay. Yeah. Before that, I'll say sometimes called middleman attacks. Okay. Are you studied, Mehak?
No, sir.
You not studied. Okay. What happens? See, na, alpha power x, alpha power y, alpha power x send by Alice to Bob, right? Alice sends this to Bob, right? And Bob sends alpha power y to Alice, correct? Right? But Eve can get this, na? Eve is getting, am I correct or not?
Yes, sir.
Eve is getting all this. So Eve, what she will do? Uh, so alpha power x is traveling. She will pick up here, right? She will pick up alpha power x and do some power z here and sends to Bob. What she will sends now?
Alpha power x.
Or even she may sends this part alpha power z, let us say. She will not send alpha power x, she will send alpha power z to Bob. Now what is Bob has? Not like that. Okay, 1 minute. What is the time saying? Alpha power x is taken and alpha power x z. Okay. Let us look at that. Alpha power x power z. Okay. So let us see. Let us see. Check. Alpha power x power z. You choose some z. Now what Bob will receive?
Alpha power x.
Yeah. But what Bob will do later? Instead of alpha power x, now he got alpha power x z. Am I right?
Yes, sir.
Now what Bob will do? Bob के पास y है ना? So finally, we will get alpha power xyz. Am I correct?
Yes, sir.
What now? Again, Eve do alpha power y. Bob is sending, right? What Eve do now? Can you guess? He will send alpha power y power z to Alice, right? Are you okay? Mehak, you are not answering. What happened?
Yes, sir.
See, alpha power x, alpha power y are known to Alice, right?
Yes, sir.
Now, what is that Eve is doing? He took some z. She took some z and alpha power x power z and alpha power y power z. Then what now Alice will do now to this?
XYZ raised to
Yeah,
XYZ.
power x she will do, right? So she will get alpha power x y z. Now what is the common key between Alice and Bob now? They do
Alpha
not know.
power XYZ.
But Eve also knows that alpha power x y z.
He knows alpha power YZ and alpha power XZ.
Yeah. So is there a way now create so that Eve also knows? Now another question I'm asking. Is there a chance that instead of this, what happens if you send see okay, here also same problem is coming, right? We are not getting anything. Alice and Bob knows now alpha power xyz bit alpha power xyz, but now Bob still sorry, Eve does not know. Eve knows only two things, alpha power xz or alpha power yz, correct? But xyz still same problem. She is not gained anything with this. But what happens if you do some modifications? Can you come up? Okay, let us see. So LIC is sending alpha power x. But what is, sorry, Eve? What Eve do? Can you guess? Alpha is public, na? So she will compute alpha power z, correct?
Yes, sir.
Bob sends alpha power y, right? Again, she computes alpha power z only. Now she sends to Bob. Now Bob, what he will do?
Alpha power YZ.
Alpha power yz. Alpha power xz. So it is also not working. Somewhere I made a mistake. So middleman attack I forgot actually. So that actually she's sharing same key with them. That's what I want to convey. But if he sends like this, then alias contains alpha power x. These two are also not equal. So even key is not exchanged properly, right? So is there any other way? Can you think of what we can do so that she knows all the three will choose the same key? Okay, think about, I will also come up. Okay, is the question clear to you? Of course, these two attempts are not worked, but I am saying that there is a method. So that Bob will do, sorry, Eve will do something so that all the three will have the same key. So that they do not understand this, Alice and Bob. They keep sending, and Eve also gets everything, that key. And now she will, since key is exchanged, so she can get everything. Okay. Now based on this, we have this the Elgamal.
So,
Yeah.
if Eve multiplies that uh,
Hmm.
alpha power x
Hmm.
sent by Alice to alpha power z,
Hmm.
then Bob will receive alpha power x plus z, right? And he will do alpha power x
But
plus z power y, that is into y.
uh-huh.
And then he will send Alice alpha power y plus z,
Okay.
and then both will get the same thing, right? Alice will do alpha power x into y
No,
plus
no.
z.
But
So
X U does not know X. No? U does not know Y independently. Correct. So how she will get the
no,
common?
uh, Eve knows alpha, right?
Eve knows alpha. Yes.
So Eve will multiply alpha power x by alpha power z.
Alpha power Z. Okay. Alpha power X plus Z. Okay.
So Bob will receive that.
Hmm.
Bob will
Bob
do
and
alpha.
Alice. Bob and Alice. Okay. Bob will receive this. Okay.
So
And
Bob will do power y to that.
yeah. So alpha power Yx plus alpha power YZ will get. Yeah.
Yeah. And again, Eve
Uh,
will give
Send
Alice.
Y plus Z, and she will compute alpha power XY plus alpha power XZ.
Oh, x z.
Yeah,
Okay.
yeah, they are, this will not work.
Yes, yes, yes. Okay, fine.
Hmm. But anyhow, we started thinking, that's good. So we'll see some approach now. Maybe. Yeah, what is that I want to say, that even though she does not know, she can manipulate something so that all the keys will be same. Both the keys will be same. That is middleman attack. That I want to convey. So I will tell you nearby. Yeah. Okay. So the Algamal public crypto system. You remember this?
No, sir.
We done it, but just recall fast. So Algamal public crypto system, how it goes. So any crypto system has two things. One is that key exchange first, right? Key exchange. Then encryption algorithm, right? I'm just recalling everything again. So in RSA cryptography, so n equal to PQ, they will Bob will choose two big primes P and Q, multiply and evaluates E comma phi of n is equal to 1 and ED equal to 1. So E will announce E and N comma E as public and D is private, right? Then that is key exchange. Afterwards, LS computes M power E and send it to Bob, and Bob will do M power E power D. Then you will get the original text back, right? That is encryption algorithm, right? Similarly here, okay, I reversed little fast way regarding it. Now how this will be done, okay? So what is key exchange and what is encryption algorithm here, right? We need to understand them. So I'm just recalling, we done it earlier. So Bob chooses large prime P, right? Large prime P and alpha a primitive root modulo P. Yeah, and computes beta equal to alpha power a mod P, where a is random and secret. So it will not reveal. Okay. So A is secret. So now what is the key exchange now? What is public key? What is private key? So public key is alpha, beta, and P. What is private key?
A.
A. A is the randomly she choose and compute it. So why it is difficult to compute A? We know that beta equal to alpha power some A mod P, right? Beta equal to alpha power A mod B, but computing A from this one is a discrete logarithm problem that is hard. That's why we are happy to send via channel so that no one will reveal. Yeah. Now public, what is LIS2 now? So now coming to the encryption scheme, right? Encryption algorithm. So LIS downloads alpha, beta, and P, correct? Yeah, she does not know, but no problem, right? So she want to send some message M, yeah, what she will compute, okay? LS chooses secretly. So this is the difference between our RSA algorithm and here. In the RSA, LS will not choose any secret key, yeah. But here she chooses secretly random integer K. But that not create any problem for the Bob to decrypt. That is the beauty of this random integer K. Yeah, okay. Now what she will compute LS? What is that LS know now? What she downloaded alpha, beta, and P, right? It is known to everyone. And LS choose some random K. Now she compute R. R is equal to alpha power K mod P. So since she knows alpha, she knows P, and K also she chosen. So R can be computed. Is it okay?
Yes.
Now T is how T will compute. She knows again beta power K, and message M is here. Message is multiplied. So now try to understand some from R from R from R. It's difficult to compute K. Do you understand
Yes, sir.
why?
Yes, sir. Discrete log problem.
Again, discrete log problem. Yeah. So this part is done. Next, look at here. So now beta power K. Beta is known. K is not known. Now, since K is not known, beta power K is random, right? Since K is random, no one knows, right? So beta power K is random. So beta power K into M is random. Even though M is chosen, but when you multiply to this, then it becomes random. So now no one knows the message also. Is random, right? So no one guess what is actually M is. Okay, so now what LS will send to Bob? What is the secret? So LI sends R comma T and also message M and message M. I am recalling little fast because we already done it. Okay, so can you recall what is R? R equal to simply alpha power K. What is T?
Alpha power
Beta power
beta
K
power K.
into M only. Very easy to remember also, not complicated. Alpha power K, beta power K into M. Mod P, everywhere mod P. Yeah. Now what is that Bob has? Bob is the person created, na? Bob created alpha, Bob created P, Bob is the person chosen P, Bob is the person created beta, and Bob is the person to create beta has A. All these are with Bob. Okay. Now and now what is that now another two now he got. What are those he? What is that other three he got? Message M he already have.
RT.
Message we need, sorry. Message M we should not send. Sorry, message I made a mistake. That is discrete. डिजिटल सिग्नेचर पे ऐसा होता है सारी हाँ बहुत मैंने बहुत गलत किया message we are now it is encryption scheme right R comma T sending from that we get the message Yeah, you are also not responded anyhow. So now Bob also has this R and S, right? It's R and S. Now R is known. So is it possible to compute these quantities? Let me know. Is it
So what
possible?
is S?
Yes, mate. T. Yeah, thanks. Yeah, yes, R comma T, correct. Why I wrote this? R comma is general R comma is right. That's why I came. Yeah. Alpha P, beta A, R, T. These are created by the allies, right? Now, so T into R power minus A. T is known, A is known, A also known to Bob. So R power minus A. What is this? What is T value?
Beta power a minus a into
Yeah. So tell me now what is that? What is she will going to get here? That is just decryption. You see, I will get it or not. Okay, so I'll compute here. Are you computed or not computed? I don't know. So T value you know, M into beta power K, R value you know, alpha power K, but power minus A is there. And beta you know, beta equal to alpha power A. So can you guess something? Okay, you know, I'm doing that now.
This will be M.
Yeah. So you already computed. I'm verifying it now for you. Okay. T power minus A is equal to, so beta power K into M. That is the beauty. Without knowing K, see, now no need to know about K. Yeah, that is a beauty. That's a wonderful thing here. So here alpha power, R is alpha power K. You remember, right? Alpha
Yes.
power alpha K minus, now I'm doing minus A here. But beta is alpha power A. Yeah, that is the beauty, right? These two gets cancelled and I got my M. Yeah, mod P, of course, everyone. Huh? Yeah. So in every case, what is happening if he's if he finds if Eve finds A, then what happens? What she will get?
Beta and alpha.
No. See, beta, alpha, P, R, T known to Eve also, right? What that Eve knows, fine, right? Public wala alpha, public wala beta, public wala P, pehle. Now R and T also, they are all made public. But from this message getting only Bob only can do because he only knows A. Suppose Eve knows A, then automatically he also get like Bob, right? That is how do you
Yes, sir.
what she will compute? He computes now T into R power
R to
minus
the
A.
power minus.
Very good, yes. But for example, she knows K. Somehow she is close to allies and somehow she grabbed K, cheating or whatever you say. Can she get M again? What is what she knows T? Yeah, she knows alpha, beta, P, and all these things. And
No.
what is T? T? Can you tell me T value?
Beta raised to K M.
So now once Eve knows K, then what she will do? Beta also she knows. Eve knows beta. Manlo Eve also knows K and Eve knows T. And Eve knows the algorithm. Eve knows the algorithm. Algorithm is known. That is also beauty about this cryptography. Yeah. Now can you say? So she knows Eve knows T, Eve knows beta, Eve knows K. So minus K he will do. What is the answer we will get? What is T into minus beta power K?
Yeah,
M. Yeah. Because T is equal to beta power K into M. So again we will get M, right? Both the cases he will get. Is it interesting? Secrets are A and K. I'm telling you that Eve knows any one of them, she will get the message. That is what I want to convey.
Yes.
Is it too clear to you, Mehak?
Yes, sir.
Yeah, good, nice. Now let us look at these discrete logarithm problems, certain things. Na? Okay. Yeah, good.
This was Elgamal, right?
This is Algamal crypto system.
Crypto
Yeah.
system. Okay.
Crypto system is not, it sends the message secretly. What is the crypto system contains two things: key exchange pehle, public key, private key.
Yes.
Of course, first key exchange, then by using key exchange, other person will take the public key, take the download, and then encrypt the message and send. And other person know the private key and she will decrypt. He or she will decrypt. Is it
Yes.
clear?
Yes.
And Elgamal public crypto system based on the discrete logarithm problem. See what happened. These Diffie and Hellman, right? Diffie and Hellman, they given the they explained the public crypto system, but they do not know that how can you do the decryption. For decryption we need hard problems, but also we need some trapdoor information, correct? So that decryption possible. So but they are unable to come up. Then so many people tried, and RSA crypto system came first, even though these are the people actually told public crypto system, but they unable to give. Then Algamal gave their system only. But RSA people, what the system they used? They even not used Diffie-Hellman key exchange, discrete log, but they used factoring problem, right? But this Algamal used Diffie-Hellman, whatever the key exchange they gave, from that they created the public crypto system. So beautifully this R and T and introducing K also. That is a very ingenious. Is it okay now?
Yes. Sir.
Yeah. Any questions, Suresh?
No, no, sir.
Yeah, everything fine? Yeah, okay, good. Okay, now let us discuss a little bit about this um, discrete log problem. So you understand that importance of discrete log problem, that's it. Huh? Suppose I have this beta is equal to alpha power x mod p, okay, mod p. So where alpha is a primitive root. Alpha is a primitive root. Okay. So now show that it is easy to compute. It is easy to compute parity of x. Parity means even or odd. Even though we do not know x, it is easy to find parity of x. Is the question clear? Okay. Hope it is clear. How we can find the parity? Now that is a question mark, right? So what do you know about this p minus 1 by 2 square? Yes, please. Alpha is a primitive root. So what about alpha power p minus 1? Am I audible? Hello?
Hello.
Okay. Yeah, am I audible?
Hello.
Hello? Hello, am I audible?
Yes, sir. Yes, sir. No.
Okay. Now what is alpha power p minus 1 by 2 square? That is alpha power p minus 1.
1.
1, right? By Fermat's theorem. Yeah. And also alpha is a primitive root. So order is also equal to p minus 1. This
Yes.
is true for every element, but any element which is relatively prime to p. But here its order is also p minus 1. Anyhow, this is 1 is fine, not a problem. Correct? Now coming to this question, right? So beta power p minus 1 by 2. Now I'll compute. Beta power p minus 1 by 2. Why I'm computing? Let us see that. This is the thing. So beta power, this is equal to, you know that this is alpha power x. Beta is alpha power x. Power p minus 1 by 2 modulo p. Yeah. Now this is equal to what?
alpha power a, right? Yeah, x.
X, I took A na. No, X only.
Okay, okay. Last problem.
Maybe earlier, maybe I took like that. Yeah. Yeah. Okay. Now, what is that happens? This is equal to alpha power p minus 1 by 2 power x mod p. Right? Yeah. Yeah. This is congruent to what is this quantity? You know that alpha power p minus 1 by 2 whole square is 1, right? But alpha power p minus 2 now becomes plus or minus 1. But can be alpha power p minus 1 by 2 can be plus 1.
Hello, sir. Your voice was breaking.
Oh, my voice is breaking. So I'm saying that alpha power p minus 1 by 2 square is 1. That you know. That means alpha power p minus 1 by 2 is plus or minus 1. Is it okay?
Yes, sir.
But alpha power p minus 1 by 2 cannot be minus 1. Why? 1. Why?
Yeah, because alpha is a primitive root.
Primitive root. So its order is p minus 1. So it cannot be 1 before that. So it is minus 1. Minus 1 whole power x mod p. Okay. So what is that? I have beta power p minus 1 by 2 is congruent to minus 1 mod p. Now what is that from this how what is that I get? Okay. So everyone knows beta, everyone knows alpha, everyone knows p, right? Now I can compute beta power p minus 1 by 2 because I know both beta and p. So if it is even then and it is odd then what happens, right? But I computed that beta power p minus 1 by 2 is congruent to minus 1 power x mod p. Is it okay?
Yes, sir.
Now, but I can do this power easily. There is a techniques. Doing power is easy, modulo p. So if this is even, my x is even, right? Not even actually. What is that I want to tell? Plus 1 or minus 1, sorry, not even. Beta power p minus 1 by 2 is plus 1 or minus 1 depending upon
Hello.
beta. Okay, again it is breaking.
Yes, sir.
Sorry, actually today I am in my home actually. University, I'm not in university. So signal may be weak. See, beta can be primitive root minus 1 or plus 1. Are you agree?
Yes, sir.
Quadratic residue or quadratic non-residue. There are only two things will be there, right? Beta. So beta power p minus 1 by 2 can be minus 1 or plus 1 by Euler's criteria. You maybe remember that. Okay.
Yes, sir.
Yeah. So that's why it is easy to know that parity of x easily. Yeah. Even though we do not know x, discrete log of beta, but we know parity of x easily. That is what I want to convey. Yeah. Now I'll do one more problem, right? For example, if Alice knows, if Alice uses some random key, k, you know that while in algorithm system, algorithm crypto system, while sending the message, right, Alice use some random key, k, right? For two different messages. M1, M2. Are you following? Like what is the time saying? I'll explain if not. See, for each message, Alice generally choose different keys, k. You remember that she uses some k?
Yes, sir.
Yeah. So Alice will choose while sending message, Alice will choose a random integer k, right? That k, suppose she is sending two messages with the same random key, what happens? Yeah. I'm giving some information here. So that is the first point. And for two different messages, M1 and M2, and also Also Eve knows M1, suppose. See, it may be possible that first Alice communicate with M1, like something like that, or otherwise suppose that Eve knows M1, then Eve can compute M2 also. So this is the question. Yeah. So I will tell you the problem, what is given to you, so that it will be clear, right? So it is Elgamal crypto system. So we have public P, alpha, and beta. These are public, correct? And what Alice will do now, right? She has two images, M1 and M2, right? Message M1 use करके and random key K use करके what she will do? She will compute R. What is R value? Remember?
Alpha power k mod b.
Alpha power K, right? Okay, I'm not writing mod P. Yeah. And for message 2 also same R she will be do, right? Since I'm using the same random key I told. But what is a T value? So I am calling T1 now, right? Because messages are different. What is T1 value?
Beta power
K
k
into
into
M1.
M1.
Yeah, of course, modulus is there everywhere. Okay. So this is again beta power K into M2, right? That's why I wrote T1, T2, but I have not changed R1, R2. I know. So hope it is clear to you.
Yes, sir.
Yeah, good. So now we have these things. How Eve can get now? Eve also knows. I gave these things, right? Eve knows M1 also. Now what is that Eve know? Let us work, have with us. P, alpha, beta, yeah, R, T1, T2. Yeah, these things are known to her. And M1 also known to her. Right. And now let us go one by one. So can you tell me what is this value? What is T1 by M1?
Beta power k.
Oh, very good. Thanks. Very fast, very quick. It is also equal to something related to T2 M2. Yes. Beta power k is also equal to what?
T2 upon M2.
Yes, correct. T2 upon M2 also. Now, now I hope you understand. So what is the need for beta power k for me now, right? I want to find M2. Can you tell me what is M2 value? T1 into?
Beta power minus k.
Oh, no, beta power k minus k I do not need. I do not know also. See,
Oh, okay. M2 is equal to
T2 m1 by t1.
T1, T2 M1, yeah, T2 M1 by
T.
T1, right? M2 into T1 equal to M1 into T2. So see, Eve knows M1, Eve knows T2, right? Eve knows T1. He knows M2 also. That is my point. Is it okay?
Yes, sir.
Yeah. So these are certain small problems on these, okay? Analysis section. Yeah. Yeah. So now I go to other concepts. Today I'm only doing this much only, discrete logarithm problem, right?
Hello, sir.
Yeah, yes, please.
How does he knows T2? T2 is beta power k
No,
into
T2,
M2, right?
T1, R, T1, R, T2, they will send now.
Oh, okay. He knows that too. Okay.
No, that is, see, Alice, what she sends R comma T, right, to Bob.
Yeah, T1, T2.
While sending means Eve knows them.
Okay, right. Okay.
Eve, he has that power and the channel, whatever going on, she will get it. See,
Got it, sir.
but this alpha, beta, gamma, they alpha, beta, P, public means it is available in the Bob's website. Alice will download alpha, beta, P from the Bob's website, and she herself choose some K and computes R and T in general. But here I told that two messages M1, M2. So she will compute RT1, RT, and she using the same random key K. And also once one of the message is known, then easy to know other message. That is the problem here. Yeah. Okay.
How will Bob know M1, M2?
Bob will know M1, M2 because see, Bob will compute by using A.
1, 1. Okay.
Bob
by
will
one.
use Bob will get both M1, M2 without even he does not need to know M1 also,
Okay.
because he is the person created alpha, beta, P and A, secret A.
Yes, sir. Yes.
Yeah, that is encryption se aayega. This is Eve. We are telling that what are the powers Eve can have, having some knowledge. That is the problem. Huh? Yeah, good.
Yes, sir.
Thanks
Got
for,
it.
yeah. But anyhow, thanks for asking. That will help actually. Yeah. Now by using Elgamal system, Elgamal crypto system and RSA crypto system, we discussed digital signatures earlier. Okay. Today I want to give you one more digital signature. Afterwards, again, I'll come to these problems. Otherwise, I don't know. Time may not be there. First, let me complete this so that I will be happy. Digital signature part I completely covered. Actually, I waited that Shubham may complete it. Yeah, that's why she till now waited, but still I don't know whether he is doing this or not. But right occasion to tell you, because this is related to Elgamal, but little modification they done and they made it's very standard now. This is the signature, digital signature everywhere used, but it is not Elgamal as it is digital signature, but they modified little bit. I will tell you. Some people call this as digital signature standard because this is the one we are using, digital signature standard, right? Yeah. So many problems here is like that. These are explaining some method. So it is like explaining an elephant. I told you earlier, right? But they are interesting how these thoughts came to them. That is more interesting. But somebody's method describing is like a describing elephant. Okay. Yeah, this is digital signature scheme. Okay. So that means that somebody will sign the message, other person verify it. So there are two algorithms. One is signature algorithm and other one is that verifying algorithm. Those who attended, they know it. Yeah. Okay. So now I'm telling you step by steps. Alice finds. Yeah. Take a deep breath and digital signature standard and try to understand. Alice finds a prime Q. Prime Q. That is around. That is 160 bits long. Okay. And chooses a prime P. That satisfies Q divides P minus 1. The discrete log problem. The discrete log problem will be hard for P. Yeah. Okay. This is the first thing.
Hello, sir.
Yeah.
160 bit prime Q. The what does that mean?
Okay.
The length of
160 bits long.
so length of that is
That many digits or something like that. If you convert it into digital or whatever. So actually it is very big. Q is at least this much length is there, but it is related to some complexity theory. But don't worry that much. So she will choose some prime and she will choose another prime. She choose some prime such that, and another prime P says that Q divides P minus 1. Now P is large.
okay, sir.
And there this P has a discrete logarithm problem for P is very difficult. So P is much larger in compared to Q. That is the first one. So It is possible, right? See, so can you tell me some number? So prime and that 2p plus 1 also prime. P is prime, 2p plus 1 also prime. 3 will work, right?
3 and 2.
So like that. So many primes. So it is possible. Yeah, not a big problem. Yeah. So for a prime p, there is another prime q. For prime q, the another prime p says that q divides p minus 1. There many will be there. We'll choose the one for which discrete logarithm problem is hard. That is the first one. Second one, let G be a primitive root modulo P. Let G be a primitive root modulo P. Yeah. Okay. Now here the beauty comes, or modification comes. Alpha equal to G power P minus 1 by Q. So now alpha is no longer a primitive root. Because alpha power Q is how much? Can you guess?
1.
Yes, 1. That means in particular actually order of alpha equal to Q only. It cannot be less also because G is primitive. Yeah. So this is the second step. Yeah. Now coming to third point. So Q, prime P, then alpha chosen, right? Alice chooses a secret A such that 1 less than or equal to A less than or equal to Q minus 1. Okay? And calculates beta is equal to alpha power A mod P. So discrete log problem coming. Beta equal to alpha power A mod P. Now fourth one. Alice publishes P, Q, alpha, beta, right? Keeps A as secret. So this is the overall key exchange here. Now Q is also extra here. Alpha is not primitive root, but alpha is alpha power Q equal to 1 mod P. So there is no primitive root now, alpha, beta, P, Q, alpha and beta. So instead of primitive root, now I have alpha. Alpha power Q is 1. In particular, alpha is a primitive root modulo Q, like that. Not Q, sorry. Not primitive root, sorry. Power Q is not, power Q, not primitive root, sorry. So now how to, so somebody takes these public and they will send a message to allies. Now how allies signs it, signs the message. Allies signs a message M, okay, by the following procedure. What is the procedure she will follow to sign the document? Select a random secret key K.
Hello, sir.
Yes.
Can you scroll up for a minute?
Yeah.
Just
Right.
got some
Yeah.
problem. Okay,
So.
okay. Yeah, I saw this. Okay.
And LS, so now actually now signature procedure. So LS,
Okay, yeah.
LS publishes P, Q, alpha, beta and keeps A as a secret. That much is done. Now signature, how it goes. Okay. She selects a random integer K, step 1. I'll come back again. Okay. Because this is, we need to explain, right? We'll forget. Yeah. This is the first step. And the second step is that how she's signing. Okay. So again, she computes R value. So alpha power k modulo p, alpha power k modulo p, and modulo q also, and mod q. This is little different here. Actually, this is the signature scheme people are using. That's why I'm just telling. S equal to k inverse m plus AR. This is similar to Algamal signature scheme. Achala and they explained. I also explained. She explained for the ellipticals. I told general. Yeah. So this much is done. So I'm not saved it. Okay. Now fourth one is that LI signature for M is R comma S. Okay, which sends to Bob along with M also. Okay. Now Bob has to verify. Message is there, signature is there. This is signature. So this is signature and this is message. Yeah. Yes. Okay. So now for Bob to verify, he must download not only Bob, anybody can do now. Okay, that is the thing here. LI is public information. What is public information? P, Q, alpha, alpha and beta. Computes U1 is equal to S inverse M mod Q. Yeah, and computes U2 is equal to S inverse R mod Q. Yeah, also computes V value. So a little complicated, but this is the procedure people are using. But I'll explain you. So not a problem. Beta power U2 mod P mod Q. Yeah. Accept signature. Accept signature if and only if V equal to R. Yeah. So since V she computed and R is already she got. Why R got? R Alice signature sent na. Alice sent R comma S and M to Bob. Okay, so what is that Bob actually has now, right? Bob has P, Bob has Q, Bob has alpha, beta, R comma S and M, right? So he computed what? U1, U2 and V, right? Now a verification is over when V equal to R. So I'll tell you why it is verified, okay? So first of all, you see that M is equal to minus AR plus KS mod Q. I'll show you. This is we done earlier. See from here S equal to Sometimes I'm writing S like this, but I hope you understand. Say a single S only. So Ks is equal to M plus Rs. So M is equal to Ks minus MAR mod Q. From this we have M. Yeah. And S inverse M equal to minus AR S inverse plus K mod Q. Right. So that means that K value is equal to, of course, congruence is everywhere. S inverse M plus AR S inverse mod Q. Right. But what is S inverse M? U1 is S inverse M, U2 is S inverse R. These two just, yeah. So this K is equal to U1 plus A U2 mod Q. Yeah. Now it is easy to check. So what is the time? I want to say that alpha power K. What is alpha power K? Remember? In general, what is alpha power K? Pehle kriye. LI is computes, na? Alpha
R.
K R. Yeah, it is R. Okay. Yeah, keep that in your mind. But now K equal to this we got, right? So U1 alpha power U1 into alpha power AU2. So alpha power U1 mod Q is there. Yeah, I'll write better, right? Yeah. So alpha power K is equal to alpha power U1. Now here inside alpha power K is beta, right? Beta power U2 mod P. So alpha power A equal to beta mod P. That's why inside mod P. Yeah. Mod P. Yeah. Is it the value of V you got?
Yes.
What is it the value of V we got earlier? Let us see. Alpha power U1 into beta power U2 mod P mod Q, right? So if you compute it, we got that much. So we got R is equal to V, verified, right? Verification happens. If it is true, it will be verified with those secret things. So this is digital signature standard or digital signature verification. Yeah. So I told you earlier, sorry for this. This is a method used frequently. So you need to know how people are using the digital signatures. It is that much only. So I'm not going into details. Just for my satisfaction, I completed syllabus. Yeah. But I'll now back to the digital signatures. Huh? Yeah, but I'll take some small break and then I'll continue. Yeah. So can we start at 9:50? Some 7 minutes gap. Yeah, 9:50.
Okay, sir.
Yeah. Right. So now I'm going to tell you that the discrete logarithm problem is hard, we know, but are there some cases where it can be evaluated easily, right? So I'm talking about, see, this P minus 1 has all small primes. P minus 1 is divisible by small primes. In that case, it is easy. Yeah. So there are certain cases where discrete log problem is not hard. We need to take some precautionary measures. Okay. Anyhow, so I will tell you some one method. So people call it as a baby step, baby step and gain step.
Hello.
Yes, yes. Am I not audible?
Yeah, voice was breaking.
Breaking, huh? Okay, 1 minute. Now is it okay?
Yes.
Yeah, okay, thanks. Yeah. Baby step and gain step, but this is given by Shanks, okay? One scientist, Shanks. So Shanks algorithm. Yeah. Okay. What is this? Okay. In the Shanks algorithm, we a priori will assume that there is a cyclic group G. There is a N. There is alpha and there is beta, right? So goal is to compute. So beta is equal to alpha power x, right? So goal is to compute this x, correct? Yeah, goal is to compute x. So how to compute it? Yeah. So the first step in the Shanks algorithm is that he computes m is equal to greatest integer function of square root of n. Okay, is it okay? What is n? Order of the group, cyclic group n. Yeah, am I clear? Yeah. So second step is that for j is equal to
Hello.
yes, still breaking. His voice is breaking.
No, sir.
Yeah. So 0 to m minus 1. 0 to m minus. What is m? Square root of m. Okay. Yeah. So j is equal to 0 to m minus 1 and compute alpha power mj. Yeah. So j is varying, j equal to 0. I'll get 1, right? What is that we are computing? Can you guess? 1. Next alpha power m. Next one alpha power 2m up to what is the last value? Alpha power
-1.
m minus 1 into m. Yeah. So these are gain steps because I'm computing power m already there. That's why it is a baby step, gain step. It's gain step. Yeah. Directly we are evaluating alpha power m, alpha power 2m. Big steps we are taking. Yeah. That's what gain step means. Yeah. And not only that. So now write these are write m ordered pairs ordered pairs j comma alpha power mj. Um, order the pairs, write m ordered pairs with respect to, okay, so order with respect to second coordinates. Means we are sorting. Depending upon the value of alpha power mj. So we are doing modulo p, right? I did not write, but modulo p. So modulo n, sorry. So when you do modulo n, then automatically they may repeat, right? They may get other numbers. So we'll order them. So obtain, and we'll call this obtain this list L1. Yeah. Obtain list L1. Yeah. So nothing actually. First we computed m square root of n, and we taken value j is equal to 0 to m minus 1. We computed these values and we ordered them based on the second coordinates, and we'll call final list as alpha, L1. Yeah. Now second one is that now for I is equal to 1 to m minus 1 now. Yeah. So compute beta also, including beta into alpha power minus I. Yeah. So some textbooks will write here minus mj, and here beta will be put here like that. So beta will be here only, but they will take plus I. So yeah, but don't worry about that. Yeah, but this is better. Beta times alpha power minus I. Sort again. Yeah. So better here also I'll say that, but instead of write, better I say sort. Sorting. So 5. Sort m ordered pairs. I comma beta times alpha power minus I with respect to coordinates. Respect second coordinates. Call list L2. List L2. Yeah, so we got two lists actually. J alpha power j I beta into alpha power minus I. Nothing actually. Very easy this step. Yeah. So now sixth one, what we do now, that find a pair. Find a pair. Yeah, I comma y, j comma y. J comma y belongs to L2. I comma y again belongs to L1. L2, L1, L2. Yeah. So, but I choose this value is same. You see that they will coincide at least at one point. So that is what I took. Now what happens in that case? So y value from the first one is that alpha power mj, correct? Which is equal to, from the second, what is the y value? Beta times alpha power minus I, correct? Mod b. So from this what happens? Alpha power mj plus I is congruent to beta mod b. So I got my almost x, right? So we can associate log beta alpha as mj plus I. Is it okay? But of course, what is the problem happening? So we need to compute powers and all this now. We need to compute m first. So if my n is very, very large, then m is also very large. Computation becomes complicated. But it is a small problem, small primes and all, then I can work out. That is the idea. Is it okay? I told for general n, but you can take a prime number here. My n is prime. Is it method is okay?
Yes, sir.
Yeah, but only thing is that why these two are equal, that equal to happen, that happens. You can easily check it. So I'm leaving that small exercise as exercise to you. But time permits, I'll come back to it. Yeah. So this is called baby step gain step algorithm. Now I'm going to tell you another one. So I'll give more examples to that. With that, I'll stop also. Not only this class, in this course as well. Unless you have some more questions. Yes, okay. Yeah, this is interesting problem. So this is what we called Polik Hellman's algorithm. That Diffie-Hellman only. They given, but they later they're trying to how to evaluate alpha. Is there any possibility? They're trying that way. Yeah. So I'll tell you things very clearly. So first, let me go very simple way. Let G be a cyclic group of order n. Yeah. Concentrate. Don't worry about the previous knowledge. Tell me what you studied today. Just concentrate from here with the generator G. And an element H belongs to G. Suppose n is equal to product I is equal to 1 to R Pi power Ei. Yeah. So that also given. Yeah. So this much we have. So what is our output? So this is input. What is output? Output is the unique X. The unique X belongs to 0, 1, 2 up to n minus 1 such that G power X equal to H, right? Yeah, see, G is a generator, so H is an element in the group, so H can be written as G power X. So discrete logarithm problem, I have to find X. So this Polig Hellman algorithm will tell you how to compute X when my n is very small. These primes are very small. The prime factorization, what are the primes which are if they are small? Yeah, okay. I'll tell you now. Right. Okay. So for each I belongs to 1, 2, 3 up to R, right? Do the following. The first step is that compute GI. What is GI? GI is equal to G power n by Pi power Ei. Okay. What is G? You remember what is G?
Generator.
Generator. So then what is the order of this element? If I do power Pi power Ei, what I will get? Huh? See, n by this one, right? If I enter power, if I do Pi power Ei, what I will get? 1, right? Power n will get, and G power n is identity. So order of GI is how much now? What is order of G1? N by P1 power E1. What are these PIs? So this is in the prime factorization of n. Yeah. Okay. So first compute GI. You will understand what I'm doing in just in a while. So now compute HI is equal to H power n by Pi power EA again, right? Now you can easily see that this HI now belong to idle subgroup generated by GA, this GA. Because H is in the cyclic group generated by G, the HI is in the cyclic group generated by GA, right? Now my problem now boils down to this particular thing. Yeah. Now in which group I am? Both this HI and GI are in the group of order n by P power I. Sorry, order I made a mistake, right? You are not telling. Yeah, okay. I'll write properly. Pi power A only. Yeah. Now I'm in this work. See, n is equal to P1 power E1, like that to PR power ER. But now one I particular I pay, I took, right? Now this HI is in P1, H1 is in P1 power E1, G1 is P1 power E1. So I am in the small problem now. So now discrete logarithm problem I am computing for this n के लिए, P power I, P power I, power prime power के लिए. So now this compute xi belongs to 0, 1, 2 up to Pi power Ei minus 1 such that Gi power xi is equal to Hi, because Hi is in the cycle group generated by Gi, so there is some xi. That is discrete logarithm problem for Hi in the group of cycle group of order Pi power Ei. So now I reduced my problem to prime powers. Is it okay? Yeah. Now what is the fourth step, right? So that means that solve the simultaneous congruences. X is congruent to xi mod Pi power Ei. Right? By now, by Chinese remainder theorem, I'll get a solution. That is my X. So theory wise, it's okay, but computing even Pi power A also complicated unless Pa is small prime. So Chinese remainder. Yeah. So I will explain one problem so that it will be easy for you, right? In general, how they are evaluating, that also I will give you before giving problem. How they are evaluating is that, see, we are taking a prime P. I am telling now prime case, huh? Prime case. So phi of P is equal to P minus 1. Generally, finally, we'll confine to, I told for general n, but we'll work for the prime, but now my n becomes P minus 1, right? We are working in a group of order P minus, multiplicative group, right? Discrete logarithm problem work in multiplicative group of ZP. That means whose order is P minus 1. So n equal to P minus 1. So it is equal to product I is equal to 1 to R Pi power Ei, right? So suppose A is equal to B power X mod P. So claim is find X, right? Yeah. So how do we proceed? So as I told you Hi, but I am telling here AI. AI is equal to A power P of P by Pi power Ei, okay, which is equal to, since B is equal to A equal to B power X, right? So B power X Phi of P by Pi power Ei. Now what happens is that we can write X is equal to, right, Pi power Ei Qi plus Ri, remainder by divisional error. Right? So now this becomes B power pi power ei qi plus ri into power p of p by pi power ei. Yeah. I'm telling you how to compute also, so that it will be. Yeah, so now here this p power ei into qi, this p power ei gets cancelled. So this becomes 1, and here we'll get b power ri into p of p by pi power ri. Yeah. So now this just find ri belongs to 0, 1, 2 up to pi for a minus 1. That is x is congruent to ri mod pi power a. So combine these by CRT. Okay, so time to give actually to make it more effective for people to understand. So let us have some examples so that it becomes easy for you. I'll take a smallest simple example. Okay, solve 3 power x is congruent to 22 mod 30. Yeah, what is values now? What is b, what is a, and all? Can you say? So here p is equal to 31, b is equal to 3,
3.
a is equal to 22.
Okay.
Find x. Yeah, discrete logarithm problem. Right. What is that we are doing? What is phi of p? P of 31. So that is equal to 30.
30.
That is very small. These are smallest primes, na? 2 into 3 into 5. That's why it becomes easy. Here you can easily find the discrete logarithm problem. I'll tell you how. Okay. So now do 22 power. So now let us take the largest prime here. That is 5, right? Yeah. And power 1 is also pi power ei, but it is 5 power 1 only. So 22 power 30 by 5 is congruent to, but 22 is 3 power x. So 3 power x power 30 by 5 mod 31. Yeah. Okay. But now this guy we will see. Yeah. So here we will write x as 5q plus r. Yeah. I divided by 5 and take the remainder. You know this. This is not a complicated thing. Whatever I am done earlier, now it becomes easy to understand. Yeah. Now this you bring 30 by 5 here. What happens? 5 gets cancelled. 30 power 30. That becomes 1, right? That's why it is easy for you. Euler phi function. 3 power phi of 31 is 1, right? So it is equal to 3 power r times 30 by 5 mod 31. Yeah. But this side we have 22 power 6. That you can compute. Okay. So that you can compute slowly.
Hello, sir. Can you just write in the notes that you're using Euler's criteria so we can
Okay.
relate?
Yeah. So here, yeah. So this is equal to 30 power 30 power
30q plus
3 power, sorry, 3 power 30 power q. I'll write that. This is 3 power 30 power q into 3 power r into 6. 30 by 5 is 6 now.
yes.
Yeah. So, but 3 power 30, this is 1. A power p minus 1. P is 31.
Yes, about
Now, so I can also write this as 6 only, so that it is not a big problem to understand from here to here. It is 6. Okay. Now you keep substituting the values. So take R value is equal to 0, 1, 2, 3, 4, right? And keep substituting and check when they are going to be equal. 31, so we can reduce this further, and finally you can easily see that x is congruent to 2 modulo 5 we get. Yeah.
What is
That
X?
means this x actually we need to find out, but this R is okay. See, now this value, try to understand that you remember that here, yeah, look at here. So actually I want to compute for general n, g, h, this is x I had to compute, but I reduced the problem to pa power ea. This is one of the factor of n. So there my hi value is h by n power pa power ea. Yeah. So now in this group, gi hi belong to this. So hi is equal to gi power xi. This xi is actually x. That means it is a discrete logarithm problem for pa power ei and the modulo pa power ei only. Yeah. So I'm calling that as x, but x is congruent to that, restricted to that prime only. First 5 only. So x is congruent to 2 mod 5. This is not original x. This is only when modulo 5. I had to find here. Similarly, we'll compute directly x is congruent to 6 modulo 5 as well. So by solving these two, we'll get the x equal to 17. 17 is the answer. Okay. I'll give one more problem so that it will be easy for you. One more problem. I'll little go fast and complete so that it will be easy. Now my p is equal to 211. G is equal to 2. H is equal to 41. Right. So now h is equal to 2 power x, which is congruent to, yeah, sorry, 41. Yeah, now phi of p is equal to 210, which is equal to 2 into 3 into 5 into 7. Yeah. So first we'll compute for 7, highest I am taking. So this is phi of p by 7. So congruent to 2 power x power phi of p by 7. Okay. Now x is equal to 7q plus r lele. Right. So what is that happening? So this 41 power 2 into 3 into 5 is congruent to. So here also you substitute the 7 cancelled and all. I hope that part is okay. So again here also we'll get 2 into 3 into 5 power r mod 7. So we're going to get x is congruent to 3 modulo 7. What is that? I want to say that you are keep substituting these values, right? R value. R belongs to 0, 1 up to 6 only. Very small values. Okay, so you can easily put it and check it. So then what is the value you get? That we are calling x, but modulo 7 only. In the similar lines, you can compute x is congruent to 2 modulo 5. X is congruent to 2 modulo 3. And x is congruent to 1 modulo 2. By CRT, we'll get x. Yeah. I have few more problems, but okay, I'll stop here. This is, but this algorithm very quick and gives the discrete value, provided the primes are very small. Yeah. P minus
Hello,
1
sir.
has a small, yeah, yes.
But how are you getting x? That is not clear to me.
That is actually not x, actually xi. So actually we are getting a Diffie-Hellman problem, discrete log problem only for mod phi 2. This I'm calling as x. So I want to find general x for 31 I want, not for this one, right? So here you keep substitute r values, r value 0, 1, 2, 3 up to 6 you substitute, and you will check that that is see, we started with here, see that 2 power x na.
Yes.
Yeah, so but I'm taking modulo 7. X is modulo, what is x modulo 7? X equal to 7q plus r.
R mod.
R mod 7. So R value I'm finding. I'm substituting R equal to 0, 1, 2, 3 and so on, right? R is congruent to 3 modulo 7. That is satisfying it. So I hope it is clear.
That is R, not x.
That is R only, but that X is congruent. X I'm taking X equal to 7q
Okay,
plus
yeah,
R.
got it.
Yeah. Yeah. So then we'll apply Chinese remainder theorem. We'll find for general X. Yeah. This way, this certain problems can be, discrete logarithm problem can be solved. So that's why we should be careful enough. There are algorithms to find a discrete log. So we need to choose primes in such a way that it has at least p minus 1 has at least one large prime. All primes in p minus 1 are small. Then we can attack by using baby step, gain step method, or this. There are many other methods also, but I will not tell those. Yeah, few are sufficient. Yeah, I will stop here.
Hello, sir.
Yes.
And the many lectures recordings are not there in the class.